In this lesson, we're going to be looking at polynomial functions. This whole chapter is about polynomial functions. So we're going to start off by defining what a polynomial function is. We're going to find a new way of evaluating points or finding points on a polynomial function. And we're also going to talk about this concept of end behavior of polynomials. Let's start talking about some of the functions we've looked at so far. At the very beginning, we looked at lines. They have a form mx plus b. Then we looked at quadratic functions, and they have a form of ax squared plus bx plus c, and it has a shape of a parabola. These are the simplest type of polynomial functions. Now, let's define what a polynomial is. A polynomial is the sum of one or more monomials. And a monomial is a number, or it can be a variable, or more typically it's the product of a number and a bunch of variables. So like 3x to the 5th power is a monomial. 7 times x times y squared, that's another monomial. Monomial means one, and poly means many, so that's why we have a polynomial as the sum of one or more monomials. So here's how we write out the standard form of a polynomial function. It consists of many terms, or it could consist of many terms. In this case, all the exponents here, n, n minus 1, they are all whole numbers. They cannot be any sort of fraction or irrational number for polynomial functions. So for example, we have a linear function x to the 1st power, a quadratic function x to the 2nd power. The degree of a polynomial is defined by the highest x term. So in the linear case, the degree is 1. In the quadratic case, the degree is 2. We have coefficients in front of all the x terms, and we have what we call the leading coefficient, which is the coefficient in front of the highest degree term. So for example, a here is the leading coefficient of this quadratic function. M is the leading coefficient of this linear function. The leading coefficient and the degree are very important in understanding the behavior of the polynomial function. We write it in standard form when we write it from highest degree term to the lowest degree term. So this is our standard form of a quadratic, standard form for a linear function. Let's look at some examples now of some linear functions. Each of these are linear, or sorry, not linear functions. Each of these are polynomial functions. Let's figure out what the degree is for each one of them, as well as the leading coefficient. Now remember, the degree is the highest exponent term. So we have 2, 7, and 3 as our degrees for each of these polynomial functions. And the leading coefficient is the coefficient that sits in front of these terms. So it's going to be 6, 9, and 1/2. Now let's look also at non-polynomial functions. Let's take a look at a handful of these. Now all of these listed here are not polynomial functions, and they're not polynomial functions for a variety of reasons. In this case, we have a denominator being the x squared term. In this case here, we don't see any of those kind of situations here. We see a square root of x here, absolute value of x, x to the negative 2 or x to the negative 1. Remember, the exponent needs to be a whole number, 0, 1, 2, 3, or so on. So all of these are cases of non-polynomial functions. Let's talk about evaluating, finding the value of a polynomial function. And by that I mean we have a function, and let's look at this one in particular, 2x to the fourth minus x to the third minus 2x plus 5. If I want to find the value f of 3, we want to evaluate the function when when x is equal to 3. We have two methods. The first method we already know. We've already used this method, and that's basically just plugging in the value. So if I want to find the value f of 3, I plug that into the x, and I solve, and I get 134. The second method, this is the new method. It's called synthetic substitution. So let's follow the steps here. I'm going to rewrite the function, and when I rewrite it, I'm going to be careful to write it in standard form, from highest exponent value to the lowest, and also making sure to fill in any cases or any terms that are missing. For example, this term, there's no x squared term, but I'm going to add it here. I'm going to put plus 0 x squared. Now I'm going to set up this little diagram, I guess you could say. I'm evaluating, I want to find f of 3, so I put 3 right here. Then I copy down all of the different coefficients, including the 0 here for this quote-unquote missing term. That's why we want to write it in so we don't forget it. So copy down all the coefficients, draw this line here, giving enough space right underneath here for a line of numbers. Okay, so now this is how we do the synthetic substitution. First step, just copy down the 2 all the way down here. Next step, we multiply 3 times 2 and write the number 6 up here. Then we add down, -1 plus 6 is 5. And then we repeat this pattern. We multiply times 3, we add down. We multiply times 3, we add down. We multiply times 3, we add down. And lo and behold, we get the same exact value. So this is another way of doing it, and the kind of nice thing about it is, instead of doing any high powers like 3 to the 4th power, all we're doing is multiplication by a number, adding, multiplication, adding, multiplication, adding, etc., etc. So it's kind of a cool method of evaluating a function, a polynomial function. Now again, the key thing is do not forget to put in zeros where there is a missing term. That's probably one of the most common mistakes when doing synthetic substitution. Now let's talk about graphing polynomials. When we graph polynomials, especially greater, polynomials of degree greater than 2, it's not as easy as lines or parabolas. And so we're going to talk about it in a kind of simpler way where we kind of sketch out the graph of it. We're going to be working toward, in this unit, learning how to graph the x-intercepts of a polynomial, as well as drawing and graphing the proper end behavior of the graph. So today's lesson, we're going to be focusing on this whole concept of end behavior and how that would look for a polynomial function. End behavior really means what happens to the function when x approaches negative infinity and when x approaches positive infinity. That's how to read this notation, this x arrow negative infinity. It means x approaching negative infinity, x approaching positive infinity. So when x becomes a very large number, for example, -1,000, -1,000,000, even bigger, -1 trillion, what happens to the function f of x when we evaluate it with -1 trillion? That's what we talk about in terms of the end behavior as x approaches negative infinity. We also talk what happens when x approaches positive infinity. When x becomes really, really large, like 1 billion or 1 trillion, what happens to the function? That's what we call our end behavior. I also talk about it in terms of left behavior, left end behavior, and right end behavior, because when we look at a graph, as x becomes more and more negative out here, what happens to the function? That's our left end behavior. Similarly, as x becomes bigger and bigger and bigger and bigger, moves to the right, that's our right end behavior. What happens to the function? Does it go up? Does it go down as x becomes bigger? When x becomes more negative, does the function go up or does the function go down? That's end behavior. So the key concept here is the following. For all polynomials, it's really dictated by the degree. All odd degree polynomials have very similar end behaviors. All even degree polynomials also have similar end behaviors. So for example, these are all odd polynomials, odd degree polynomials, all the exponents of the highest term, and I don't even write out the remainder. It doesn't really matter. We can just ignore all the lower exponential terms. We're just concerning ourselves with the highest degree term. These are odd polynomials, odd polynomial functions. They behave like the very simplest of odd polynomial functions, which is our line. Now, a line looks like this. We have when the function or when the slope is positive, as x gets really negative, f of x goes down. As x becomes big, f of x goes up. Now, we also have the case where we have a negative slope, or where the coefficient here is negative. In that case, it has opposite end behavior. As x becomes negative, f of x becomes very big. As x becomes very big, the function f of x becomes very negative. Now, for even functions, it has a different kind of behavior. Again, these are all even degree polynomial functions here. They behave just like the simplest of our even polynomial functions, the quadratic, the parabola that we just recently talked about. So you can see that the end behavior of a parabola is very different. We talked about where the coefficient in front of the x squared, when it's positive, it goes up on both ends. So the behavior on both the left and the right hand side is positive infinity, positive infinity. Now, when the coefficient in front of the x squared is negative, the end behavior is different. It goes down on both ends. It goes down forever on one end, on the left end. It goes down forever on the right end as well. So, conceptually, if you can remember this kind of concept here, all odd degrees behave like lines. All even degree polynomials behave like quadratics. That helps you a lot in terms of remembering what happens here. I'm going to summarize it with this other picture, and this is kind of what's in the book. When we have an odd degree polynomial, leading coefficient greater than 0, it has this end behavior as such. And I want to kind of remind you of this notation here. As x approaches negative infinity, f of x approaches negative infinity as well. So it's saying as x becomes more and more negative, f of x also becomes more and more negative. And then we have the other case here, as x becomes really big, as x becomes bigger and bigger and bigger to the right, f of x becomes bigger and bigger and bigger in a positive manner up to positive infinity. So we have the other cases here. I'm just going to show all of these at once. And again, these are kind of like lines. All of our odd degrees, this is kind of like a line, positive slope line, negative slope line. And then we have the even polynomials, which kind of has the behavior of the quadratic. We have the up u, and then we have the down u. The only difference is with the higher degrees, we have some squiggly stuff going on in the middle of it, but in the very ends, the end behavior itself will be either like a line or like this parabola. Again, the squiggly lines are in the middle are caused by the higher order polynomial degrees, but the end behaviors are stuff we've already seen. So for example, let's do a few. What's the end behavior of the following polynomial functions? First off, let us figure out what the degree is of each one, what the leading coefficient is of each one. So I'm going to highlight the highest term, and in this last one I put it out of order. 15 is the highest exponent term. So our degree here is 5. The leading coefficient for this case is 1/10, which is a positive number. So it's going to have this kind of shape here, odd degree with a leading coefficient that's positive. It's going to have this kind of behavior. And this is the way I write the notation. The left end behavior is negative infinity to positive infinity. Negative infinity on the left, positive infinity on the right. The next one has a degree of 8, and it has a leading coefficient of -4, and so that's an example of this case right here. Even degree, leading coefficient less than 0. Again, think of a quadratic. Even degree, it's like a parabola. Leading coefficient's negative, it's like a down U. Last case, leading coefficient 15, or sorry, degree 15, leading coefficient negative right here, pi over 6. Odd degree, it's kind of like a line. Negative slope line in a ways. So it's going to have a behavior positive infinity on the left, negative infinity on the right, just like this case right up here. Okay, that's our lesson for today.